Thank you, Aria, for the nice invitation. Welcome to the TILOS Institute within HDSI. So today I'm going to talk about how to make use of the reverse diffusion project for the purpose of how to make use of MCMC to accelerate the inference of diffusion models. So let's jump right in. So let's first talk about making use of the reverse diffusion project. Actually, this is joint work with Hong Zhang's group. The background of the problem is that we have a Monte Carlo problem. Because we are given a density function up to a normalization constant. We want to generate samples. So this problem appears in scientific computing, Bayesian statistics, and machine learning in general. The question is for high-dimensional posterior distribution of calculus. Right? The ideal situation, we want to generate a sample according to this true posterior distribution. Right? But in practice, oftentimes this is not practical. So instead, we can generate a sample according to an approximate and hope that we use an iterative procedure to incrementally. Right? The hope is that eventually this PT will approach the true distribution as T goes on. So this is the TILOS Institute. This is the learning-enabled optimization. So let's reformulate this problem into an optimization problem. What we want to do just to minimize a loss function between our current distribution and time. The typical loss function we can use is the Kohlberg-Levin divergence. So this is an optimization on the space of probability type of problem. Right? So for optimization problem with, let's say, a continuous structure, what's the first thing we think about doing? Right, well, what do we do with the optimization problem with a continuous variance of gradient descent? Right. So first figure out what's the gradient of the KO divergence with respect to our argument, our current distribution. Using the Water-Strang 2 distance as a metric, and the strong subdifferential of the KO divergence is the gradient, is a vector field, which is the gradient of log current distribution of the target. Okay. So it seems like we can just reformulate this into an optimization problem, which is a gradient descent. And the nice thing about it is that it's in the space of your sample. So you can directly follow this dynamics, right, in the sample space to obtain a new sample, which incrementally gets closer and closer to the target distribution. Seems like the problem is solved. Nothing else needs to be done. But is there any problem with this? And can we actually implement it? Right. So the target density is fine. We know it's up to a normalization constant, right? Taking gradient of the log, we can directly compute it. The problem happens with PT, right? So imagine that we initialize from a nice normal distribution where we know what P0 is. We follow this trajectory and we hope to get to P star. But the intermediary distributions, we don't really know this form. We have samples according to it, but to actually sort of estimate this form is costly. Right? It scales exponentially with the dimensionality. Right? So that's the problem. We don't want to do that. So there are a few ways of tackling this. So classically, one way to do it is to sort of parameterize PT, right? Constrain it into a parametric family so that we map the gradient, which lives on the tangent space of the probability space, to the gradient, which lives on the tangent space of this finite dimensional parameter space. And that's variational inference. Another way to think about this is to say that, okay, can we use an equivalent process which substitutes gradient of the log current distribution? Right. So infinitesimally, gradient log of the current distribution is the same as a Brownian motion. So we can substitute it, right? Simulate a process driven by Brownian motion, which corresponds to MCMC. Okay. So recent development in machine learning tries another approach. It says, well, what if we directly parameterize gradient of the log PT, that's for the score function, and we do score matching? Right? How does that work? So we tried it. So essentially, we parameterize this gradient log current distribution as a score function. We try to parameterize it and learn it, it doesn't work so well. So the reason is the following. If we follow this forward process, let's say we initialize from a standard normal, and then the target is a mixture of Gaussian distribution with even mixtures. What happens to the intermediary distribution is the following. It has all those complicated structure arising right, from this sort of transition process. But essentially, you initialize from a standard normal distribution here, then it will get sort of trapped into a local mode closer to the initial distribution. Right? So you need to if you want to capture intermediary distributions and a score function with respect to it, you need to capture those complicated structure. It's kind of an overkill. The target distribution don't have those complicated structures. Right? So you don't really need to do that. Right? So then what's the solution for that?
Sorry, when you say it doesn't work, in what sense is it not working? But
right.
Does it not work for mixture of Gaussians?
So we find it, for a simple distribution, just like even mixture of Gaussian. What happens is that it's slower than the distribution. Right. Yeah, it's because it's kind of an overkill, right? But we don't really need to capture those intermediary distributions, right? So then perhaps the easier way to think about this is to start at the end and go backwards to a standard normal, right? In the sense that we initialize, let's say, imagine that we can initialize from the station target distribution, and then we try to converge it to the standard normal. Then immediately we can see some benefit algebraically, in the sense that gradient of the log, now the target distribution is standard normal. So this part is already linear. Right? So the algebraically, this already looks so simpler. And then we estimate the score functions in the intermediary steps, and then rewind the whole process to get back to the target distribution. Okay. So before talking about how to implement this, let's first take a look at the pictures and see if it looks simpler. So this is what happens if you follow the forward process, and this is what happens when you follow the reverse process. If you initialize from an even mixture of Gaussians, and then go back towards the standard normal, then what happens is it stays a Gaussian mixture, right? And it's just a convolution of the original Gaussian mixture with the standard normal distribution. So it doesn't ask you to provide any more information. Okay, so then let's get into the maybe technical details to see how it gets implemented. So the first thing we realized is that the score functions, in this case, if we know the posterior distribution up to a normalization constant, they can be explicitly computed. So we don't really need score matching, in the sense that those score functions are just expectations of the linear function. And the expectation is with respect to a distribution, which is the product distribution of the posterior distribution that we care about, and the Gaussian distribution. Right, so that's all we need to do. Right, so we don't really need to do score matching if we know the posterior. Okay, so then in this case, basically what that means is we don't really need to track the process backward. We just pretend there is a backward process. We don't really need to go through that. Right? All we need to do is to estimate all those intermediary score functions in the middle, and then do a forward one. That's all we need to do. Okay. Okay, so then how exactly are we going to estimate those score functions in the intermediary then? One way to think about this is, so this is the product distribution between the target density and the standard and the normal distribution. One way to think about this is to do importance sampling, right? So we generate samples according to the normal distribution and then do important weight sampling, right? Making the weights to be proportional to the target. So this one, it kind of works. The challenge is that the variance is large if you do importance weight sampling with an unbounded density function, which can be arbitrarily close to 0. So an alternative way that's more efficient that we found is to actually generate samples using Langevin and CMC according to this product distribution. And the reason it's simpler than directly generating samples according to the target distribution is that this Gaussian part is served as a regularizer. And if we pay close attention to the coefficients, when t is close to 0, this part blows up, this part dominates. So essentially what that means is when we're close to the target distribution, this procedure is very simple. It's almost like a Gaussian. And as long as this segment length t scales like 1 over the Lipschitzness of the swirl function, this part still dominates. And this QT distribution is still simple in the sense that it's strongly log concave. So we can treat it like a convex problem. And we can very efficiently generate samples according to it. And then using those samples, we can estimate this swirl function very efficiently. Okay. And we know that when we're close to the starting point, then this PT itself is simple. So then the question is, what do we do in the middle? How do we bridge them?
The problem is the variance is still large.
So if we can generate samples according to T, actually the variance isn't that big of a problem, right? Because we just need a number of samples to estimate this swirl function. It's estimation of the median, so it's not that hard. But if we instead just generate samples according to the Gaussian, reweight it using the push theory and the variance. Right.
And that is one of the problems when T is this order of 1 over L.
Exactly. Exactly. So whenever t is small, whenever we're close to the target distribution, not a problem. Right. So then that's one way to think about it is, can we only do this thing? Do we have to do all the rest of the things? So, for example, can we change the target essentially? Let's say this is the target now that we care about, right? For the rest part, we only converge to this target. And then we initialize from this target to converge to P star. So for the rest of the segments, essentially we just do a recursive call to this function. Right, can we do that? So here the new target is, let's say T1. Then what happens is that in the case segment, we change the target here. The target now is no longer the posterior distribution, right? It's the one that's next to, it's the closest one, closest checkpoint in the segment. So that T minus Tk is always going to be on the order of 1 over L. And then to be able to run this algorithm, we do a recursive call to the previous segment. Okay, just solve this recursively. Yeah. So figuratively, this is so we solve it recursively for the score. Figuratively, this is what happens. So to be able to estimate gradient of log PT hat, we generate samples according to QT, right? And then for each sample of the QT, we generate samples making use of the swirl function in the previous segment. And then for each of the samples, we make use of swirl functions in the previous segment. So this scales exponentially with the number of segments. Right? So the key is, how many number of segments do we need? So we found that we just need L that's the difference of the swirl function times logarithmic number of segments. So this exponential dependence on L is unavoidable. There are lower bounds for that. And the rest of them scales logarithmically. Okay, so we tried this for a Gaussian mixture, simple Gaussian mixture example. And we tried to see how it scales when the Gaussian mixtures becomes further and further apart. Because there are works basically established that for anything really, the convergence time scales exponentially with the mode spread. And then we look at what's the dependence of our algorithm with respect to the mode spread. You can see that if we just use Langevin type of algorithm, so it quickly just plateaus. Actually, within a gradient complexity of 200, it doesn't do anything. The accelerated version does something, it's a little better, but still doesn't really get there. But using the reverse diffusion Monte Carlo method, it converges within about 100 sort of queries to the gradients. That's adding together all the samples gradients. And we can prove that actually there is an MCMC lower bound for those cases. And reverse diffusion Monte Carlo exceeds that lower bound. Basically, no MCMC algorithm can compare to using the reverse diffusion Monte Carlo. And so overall, the overall theorem basically says that if we can assume that scores are literally continuous and assume that the posterior has finite second moment bound, then the sort of the total computation likelihood of reverse diffusion Monte Carlo scales exponentially with the Lipschitzness, but quasi-polynomially with everything else. So this extends the horizon of the tractable problems that we can deal with in the Monte Carlo problem. Okay. Right, so that's the part with making use of the reverse diffusion process to help with Monte Carlo problems. And we can also think about, can we use the similar structure to make use of the Monte Carlo model, several diffusion model? Right. No, we assume it has a second moment bound. So this is much weaker than anything like that. Okay. So basically it can be highly multiple as long as it has a smooth structure. Right, so in mixture of Gaussians, mode spread comes into L. So the mode spread would come into actually your exponential terms. And yeah, and also the smoothness itself.
The final dependence for mixture of Gaussian will be exponential.
In the mode spread. Yeah, but we reduce the coefficient in front of it. It's not. It's all yeah. The number of components is not a big deal. The problem is
that's your detail.
that's true. Yeah, so that's nice. And there are actually laws for Monte Carlo sampling problems.
So that's exponential.
The low bound is exponential to the so there are room for improvement here. So you should be able to shave off this third one. That's something. Yes, the intermediary. Yeah. Yeah, that's a very important thing, and it's also trying to understand a little bit. So something is that PT hat, so the regularity is worse when it's to the form distribution, but moves away by a little bit. And I think it can get a little worse than original target distribution. But not that much. But that's something we're trying to figure out. Actually, yeah, I think to observe time, I think maybe I should just stop. I have a couple of days. Let's see, whether it's possible to go through the diffusion model. Yeah, I guess just a couple more. To be able to accelerate the inference behavior for diffusion models making use of Monte Carlo methods, one idea is the following. So instead of looking at the discretization of a continuous process, which the diffusion model does, instead we look at we just look at those diffusion models as discrete transitions, discrete in time transitions, right? Where you use Gaussian kernels in classical diffusion models. And then the reverse kernel is just essentially the same as what we talked about in reverse diffusion Monte Carlo. That's the sort of the current density functions multiplying this Gaussian kernel. Right. So then we can make use of techniques in MCMC to accelerate sampling according in this case. So that's how we sort of think about accelerating accurate inference in diffusion models. But that's the gist of it. I don't think I'll have much time to go into the depths of it. Thank you.